Welcome to the first of many devlogs pertaining to Inverity, a new project I've started last month based on an idea I've had for a very long time. And that idea is the main focus of this first devlog, and by extension, last month's progress. It's basically the driving force behind this whole game. In order to get a clearer idea of what that entails, we should probably start at the beginning. After returning home for my first semester of college, I began designing and programming a new game engine using C++ as the language, and OpenGL as the graphics API powering it. I've never been fond of using game engines. I appreciate the convenience and all that, but I'm one of those assholes who likes to design and have control over everything from the ground up. Or at least from a standpoint that gives me a good illusion of such a thing. After all, I'm not creating my own programming language or anything like that, at least not yet, but my efforts led me to designing a rudimentary framework for OpenGL's rendering pipeline. OpenGL's rendering pipeline essentially works by taking a series of numerical values supplied by the program on the CPU and interpreting them into drawable objects using shaders, which are programs written for and run on the GPU. This series of numerical values is usually packaged into vertex buffer objects, or VBOs, which act as attributes for each vertex of a drawable object. Things like the position of each vertex, the color, the normal vector, anything that varies from vertex to vertex. These VBOs are then applied to a VAO, or vertex array object, which is a list of VBOs that are used to create and fully flesh out different drawable objects, or meshes as most people call them. Shaders are written in a language similar to C known as GLSL, at least in OpenGL's case. And I had to also write some code to allow the program to load in text files and compile them as shader programs, as well as display any possible errors occurring with them to the console. For any graphics programmer who specializes in OpenGL, this is a pretty novice task, and I was able to get all of this done by the end of the first day of development, as I had done it several times before. However, one of the more noteworthy challenges of this development cycle is the lack of a solid external mathematics library, like GLM, which is commonly used to take care of math-related issues like a full implementation of mathematical vectors and matrices that can be used and manipulated to solve any math-related problems, such as the ability to translate, rotate, and scale meshes. Starting on December 1st, I began working on my own math library to help out with this, really only taking care of the basics, such as adding 2, 3, and 4-dimensional vectors, as well as the ability to add, subtract, multiply, and divide them at both scalar values and other compatible vector objects, and a class for a 4x4 square matrix, although all you can do with it for now is adjust each value of the matrix manually, without being able to perform any mathematical operation on it. I didn't really need to program this in, at least not yet, as GLSL already has the capability to multiply compatible vectors and matrices together. This allowed for the implementation of the model view matrices to be a whole lot smoother on my end. The model view matrices mainly consist of 3 main matrices that, when multiplied together, result in a solid 3D projection pipeline commonly used in most 3D games and graphics engines. OpenGL's default projection is 2-dimensional, and also uses screen coordinates where 0, 0 is the center of the screen, and the values of 1 and -1 correlate with different sides and corners of OpenGL's viewport. The first matrix, being the transformation matrix, distorts these coordinates such that the specified position, rotation, and scale of one or more meshes specified is displayed in screen coordinates. The projection matrix distorts those coordinates again to allow the z-axis to matter in world space, and essentially divide the x and y coordinates by the z-coordinates of the object specified, resulting in the illusion of 3D space, as the objects get closer to the center of the screen the further away they are. The projection I used was the standard that specified a field of vision, which I elected to be 70 degrees, as that closely resembles the field of vision of the human eyes. There are other projections as well, one of the most famous being fisheye projection, which is a projection that a lot of GoPro cameras appear to use, where instead of objects getting closer to the center of the screen as they get further away, they get closer to the edges of the screen. An artist might refer to the former projection as 1-point perspective and the latter projection as 2-point perspective, which is a good way of looking at it. Anyways, the final matrix is known as the view matrix, or the look-at matrix, which is used to transform the entire world based on the positioning of the player camera, and is basically a special type of transformation matrix. Keep in mind that the matrices aren't usually applied in this order. This is just the order of which I tend to create them in. Projection is usually multiplied with view, which is then multiplied with transform, and then finally the 4-dimensional coordinates of the vertex specified at the position VPO is multiplied with all of that. Okay, that was a bit of a mouthful, but now we've gone from a rudimentary framework to a more robust one, complete with entity objects which specify a mesh and apply a transformation to it automatically, as well as a half-complete first-person camera. By now it's December 4th, and finals week is about to hit. Oh yeah, by the way, I wasn't done with college, they just sent us home early because of the virus, and didn't want us to come back because of Thanksgiving family gatherings putting the campus at greater risk for an outbreak. Seeing as how finals took up most of my time over the next week, progress became a whole lot slower on this project, although I did find some time to finish the first-person camera on December 9th. After finals week concluded, I spent most of the following week recuperating and working on smaller things, like my first original song since March of 2019, which also serves as a solo debut for my new alias, Ode, which was released on December 18th. A link to that will be in the description. Progress officially resumed on the 19th, and the first visual indicators of said progress began to appear a day later. So, now that we've gotten the basic engine shit out of the way, it's time for the real deal. Boxes. Basically, this game involves the use of sectors, which, for now, are just boxes and planes, or empty air, as the game's world will end up being entirely constructed of them. It's a simplification used to make the idea mentioned earlier work in a feasible way, and I promise you'll know what this idea is by the end of this devlog. Hint, it has to do with the title of the devlog, in case you couldn't tell. At any rate, I created 2 debug objects to better visualize the creation and deletion of these sectors. The first being a cube encompassing the current area or sector being iterated upon, and the second being a white object representing the frustum. The frustum determines where a sector can or can't exist. If a location being iterated upon, again visualized by the cube, lies within the frustum, then a sector, currently represented by a small yellow box placed right in the center of it, is created there if none exist in that location already. Sectors are also destroyed if they lie outside of the frustum, as each frame a check is performed on each sector to see if it lies within the frustum or not. This method of destruction is different, as it isn't tied to the game's frame rate, and as a result is not very well optimized. I might end up adding another iterator for it as well, although after improving the system over the course of the following few days leading up to the 22nd, the issues with sector destruction had mostly vanished for now. Speaking of which, this is where the idea comes into fruition. In case you haven't guessed, the frustum will be directly tied to the player's camera, meaning the entire world basically exists within what you see. This is not too unlike the popular graphical optimization technique known as frustum culling, which basically checks all of the drawable objects in the scene and only bothers rendering the ones that the camera or player can see. This is essentially taking that concept and building an entire game around it. In Inverity, not only are sectors and objects not drawn when they're outside of the scene, they're also deleted, and when the player looks in that direction again, something new will be in its place. That's the idea. Is it practical? Well, we'll see. As I've mentioned earlier, I've made several adjustments and improvements to how the iterator that creates sectors functions. For example, it's used to iterate through different areas, and by extension, generate sectors in a linear box motion, but now it iterates around the player's position. It can also generate multiple sectors per frame, as well as completely graze the area outside of the frustum within a single frame without causing the game to stutter, though this might change with a higher render distance. Finally, a high enough adjustment to the player's frustum will center the iterator on the player, ensuring that new sectors will, 95% of the time, generate around the player's proximity. As a little demo for this, I made a basic maze generator. Well, it's less of a maze generator and more of a random box generator, but it can function like a maze generator nonetheless for my example. It's not the best showcase of what I have planned for the system, but it gives you a pretty good idea of what it can do, as well as some of the issues it still has. With that said, I'll leave you with a little bit of footage for it. Take care everyone, and I'll hopefully see you all soon. Happy holidays.